Good afternoon. In today's class, we are going to discuss a new test of significance known as chi-square test. And if you can remember, in one of my earlier classes, when we studied distribution functions, especially continuous distribution function, we studied the distribution of the gamma densities. And probably you can remember that there I gave you a special case in which the gamma densities tends to follow chi-square distribution, or you can say under some special conditions, gamma distribution tends to follow chi-square distribution. So just like binomial distribution, Poisson distribution, normal distribution, chi-square distribution is also a kind of distribution which is continuous distribution. Here we are not going to talk about chi-square distribution, rather chi-square statistic, and I'm going to tell you one of the situations in which chi-square distribution or chi-square statistic is applicable. Let us analyze this particular situation first of all in its theoretical sense. We actually consider a very large population, and from this population we want to select a sample and we want to test one of the characteristics of this sample in the following way. The population which I have selected is very large, and it is such that each member of the population has a value that can be 1, 2, 3 or k. So actually we are dividing the entire population into k different subparts. Okay. Now for a given set of probability pi, where I goes from 1 to up to k, we will consider the problem of testing the hypothesis that these pi's represent proportion of the population for each value I. So if we let that capital Pi denote the true proportion of the population for each value I, and that is these values are actually small pi's, then we are actually about to test whether these true populations are indeed equal to the assumed proportions. The assumed proportions are actually equal to the sample proportions. Let me put this particular thing in another words. Suppose you have got a situation where you have divided the entire population into several parts, and after studying that particular after these individual parts, you have come to know that one of the parts, say the first part of the population is having some characteristic with probability p1, small p1. Second part is having some probability p2. Third part is having some probability p3, and so on. Now suppose we all know that the population survey is not possible. So what actually I'm saying, that if we consider a big circle to be the main our population, then inside that big circle we are considering a small circle which is a subset of that big circle, and that small circle is my sample, and these small circles are divided into several subclasses, and each of these classes are represented as 1, 2, 3 or up to k, first class, second class, third class, and kth class. Okay, and each of these classes of the sample contained in the population is having the probability small pi. Now the probabilities which I am calculating for each subclass corresponding to the sample, these are my calculated probabilities, and since the subclasses are part of the population, so I can say that this probability small pi are the probabilities of some parts of the population. But suppose the actually the populations, if we consider these parts, the actual true population is capital pi for each of the parts considered. Small pi which we have calculated, we want to justify the fact that our true population, our true population means the assumed population is indeed having this value small pi's or not. Suppose that in another sense we can state it as we want to test the null hypothesis whether this true populations P1, P2, P3 are having the values small p1, small p2, small p3, and so on respectively or not. And if we want to test this as null hypothesis, then we have to set this null hypothesis against the alternative hypothesis that they are not. True population is varying from the sample population. Under this scenario, we use the chi-square statistic. It would be nice if I represent this particular problem in terms of an example. So let us consider the following example. It is known that 41% of the United States population has type A blood, 9% has type B blood, 4% of United States population has type AB blood, and 46% of the total population has type O blood. Now, if you add these figures, 41, 9, 4, and 46, you will get 100% of the United States population. Suppose that we suspect that the blood type distribution of people suffering from stomach cancer is different from that of the overall population. So you see the actual that I have represented here in terms of pie chart, that this is the percentage representation of the populations. So I am representing that this violet color portion represent the 46% of the population which is having type O. 41%, this blue colored portion is having the is showing you the percentage of population which is having blood type A. This red color portion is having the 9% of the population having blood type B, and this green colored portion is the percentage of the population is which having the blood type AB. So after we add this, we get the entire circle which is 100%, representing the blood types of the population. Now we want to study what is the distribution of the blood types of those patients out of this United States population, those patients who are suffering from stomach cancer. What are their blood types? We want to study it. So we have got some sort of percentage over here. So we want to set our null hypothesis in the following way. What we want to test is that if suppose the true population of related to the blood types and the stomach cancer are actually denoted by capital P1 of the first capital P1 for the first type of population, first section of the population, or the section having blood type A. True population corresponding to the blood type B is suppose capital P2. The true population having blood type AB is suppose the proportion represented by P3, and P4 is associated with the blood type O. These values P1, P2, P3, P4, these are the true proportions of the blood types. I want to test whether the values which I have obtained, actually these values are known as observed frequencies. These values have been obtained from the data after selecting some sort of example, some sort of collections have been made, and the data has been noted down. From that data, these percentages are available. We shall name those percentage. If you want to compare this example with my above statement, these values 41%, 9%, 4%, 46% are actually the values of small p1, small p2, small p3, small p4. So we want to test whether my true population is reflecting that or not. Whether we want to test whether my true population is given as capital P1 is indeed 0.41, capital P2 is indeed 0.09, capital P3 is indeed 0.04, and capital P4 is indeed 0.46, against the alternative hypothesis that they are not. And I have written specifically over here that capital P1 is a proportion of all those with stomach cancer who has type A blood. P2 is the proportion of all those patients who has type B blood having the stomach cancer. P3 is proportion of all those who have type AB blood, and P4 is the proportion of all those who are having type O blood. So the general rule to set the hypothesis will be like this. This is the general rule. You can tally these two things together. What are the steps? What are the steps by which we can proceed with our statistical hypothesis testing? Step one is that we want to draw a random sample from the population, and suppose this sample is of size small n. This is the sample size. Let capital Ni denote the number of elements of the sample that have value I. Now the sample has been denoted, what I was telling earlier, the sample, you consider this to be the small circle. This part, sample size, the number of elements present in this particular small circle contained in the big circle which represents population. The small circle is having total number of elements as small n. Now you divide the small circle into 4 equal parts, or here in general we are dividing the small circle into k equal parts. Each of these parts are having some sort of numbers. The first part is having the number n1, capital N1. The second part is having the number capital N2. Third part is having the number capital N3, and the kth part is having the number nk. So if we add these figures, n1, n2, nk, we get the total sample size small n. I hope you are understanding. Okay. If null hypothesis, which we have set over here, is true, then each of these numbers, capital N1, capital N2, capital N3, dot, 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 nk, we can treat these numbers as random variables, and these numbers will follow the binomial distribution. Okay, with parameters small n, total size of the sample, and probability of success, probability of having a particular characteristic corresponding to the subsample I, which is true for all I. So, you know, number of something, count of something can be treated as random variable by its definition. Okay. Now, for each of these subclasses in which the entire sample has been divided, let EI denote the expected number of outcomes that equal I when H naught is true. So for the first subclass of the sample, say 1, the expected number of outcomes E1 will be small n into P1. For the second subclass, it will be E2 represented by n into P2. For the third subclass, it is E3 represented by n into P3. For fourth subclass, it is E4 represented by n into P4. Okay, so all these and so on. If you divide the sample into k class, then you will write it as small ei is equal to n into pi. Now, how do I get npi? It's very simple, because we have assumed that my capital Ni is the random variable which is following the binomial distribution by rule with parameters small n and small p, small n and small pi. So expectation of Ni will be n into pi, because the mean corresponding to the binomial variate is np. From this we have got this formula. Now there is a difference between the two items. Capital Ni is my observed frequency and small ei is my expected frequency. I want to test how these observed frequencies and the expected frequencies are connected to one another. So in step 4, we have written that if H naught is true, then we expect that capital Ni, that means the observed frequency, would be relatively close to small ei. That means expected frequency. That is, when the null hypothesis is true, the quantity Ni minus ei whole square, the square of the difference of these two frequencies, shouldn't be too large, and say in relation to ei. So for each ei, that means we are actually talking about a ratio over here. If we talk about E1, then the difference Ni minus E1, the square of the difference N1 minus E1 will not be too large. If we talk about E2, the square of the difference N2 minus E2 will not be too large, and so on. Okay, so in this way, we define the chi-square test. Chi, C-H-I, it is pronounced as chi. We define the chi-square statistic in the following manner. So we write it as capital TS is equal to summation I goes from 1 to k, and the ratio, each of these ratios corresponding to the subsamples is calculated and added together. So we have written summation, and under the summation sign, we have written Ni minus Ei whole square by Ei you can say it as n1 minus e1 whole square by e1 plus n2 minus e2 whole square by e2 plus dot 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 and so on. And what is the criteria for drawing the conclusion? The criteria for drawing the conclusion would be H naught is rejected when this test statistic is sufficiently large. Or in other words, we can say that we reject the null hypothesis if the value of this test statistic is greater than the tabulated value of chi-square at level of significance alpha and degree of freedom k minus 1. Okay, so the number of independent variables in this particular case in chi-square statistics is 1 less than the subsample size. What is k? It should not be small n minus 1. Small n is the total sample size. You are dividing the sample into several subclasses. Okay, we are dividing the sample. So for example, let me show you in this manner. So this is my sample, and this is having a small n amount of items. Now we are dividing the sample into this part, this part, this part, this part, and so on. So if I can take the union of this 1, 2, 3, 4, 5, 6 parts, we'll get the total sample. Now this is my part 1, this is my part 2, this is my part 3, this is my part 4, this is my part 5, and this is my part 6. Okay, now what is the value of k here? So if you what is sample size here? The sample size is something, say the sample size is actually small n. So when I divide the entire thing into several parts, this first part is having some size. Say the size of this part is say for example, this let me write it over here, you will understand. The size of this part is size of this part is say n1, size of this part is say n2, size of this part is n3, size of this part is as n4. Let me write all this, and this is having the size n5, and this is having the size n6. So this means that when I add the figures n1 plus n2 plus n3 plus n4 plus, if I add all these things, all these numbers together up to n6, that will be equal to the total sample size, that is small n. And none of these numbers n, n1, n2, n3, n4 is k. K is actually having the value in this particular case is how much? It is 6. In this particular example which I have drawn, k is equal to 6. 6 is the number of subdivisions in which the sample has been broken. Number, how many parts are there which combine the total sample. Not the number of elements present in the parts, number of parts. So the degree of freedom in this particular case will be k minus 1, which is one part, the part minus, if the part is 6, the degree of freedom will be 6 minus 1, that is 5. So now we are going back to the problem which I was stating with respect to the blood type and the distribution of the distribution of blood types in the stomach cancer. Let us go back to the problem. Okay. So we have set the example in the following way. Just a minute. Suppose in the above problem of blood types and cancer that a random sample of 200 stomach cancer patients yielded 92 having blood type A, 20 having blood type B, 4 having blood type AB, and 84 having blood type O. Are these data significant enough at 5% level of significance to enable us to reject the null hypothesis that the blood type distribution of stomach cancer sufferers is the same as that of the general population? So here the total sample size small n is 200. Okay. Now, what are these 92, these numbers, 92 and 20 and 84 and 4? These are actually the values of N1, N2, N3, and 4. So if you add the total number, all of these, you will get, these are the numbers which actually gives you the, in how many parts the number, the entire sample has been uh, uh, divided into 4 parts, and each part is having the numbers given by this. So these are the observed frequencies. What will be the expected frequencies? Since the total sample size is 200, so the expected frequency will be 200 multiplied by the probability of each part is given earlier. We have already told the 41% is having blood type A, and 9% is having blood type B. So 0.41 is the probability. So the expected frequency for this part will be n into P1, which is 82. The expected part of this will be n into P2, which is 18. The expected part of this will be n into P3, that is 8. And the expected part of E4, that is n into P4, that is 92. Interesting to note that if you add these numbers, 82, 18, 8, 92, you will get the total number. This will be the same as 200. So expected number of items present in each part is, when summed together, gives you the total sample size, which is 200. Total of this will not be 200. Don't mix it up. Total of these numbers will not be 200, but total of these numbers, these figures will be 200. Now we have already defined the test statistic. The test statistics has been defined in the following manner. So by using this above rule, we have written TS to be 92 minus observed frequency minus expected frequency squared divided by 82. That means the expected frequency. 20 minus 18 squared divided by 18. 4 minus 8 squared by 8. 84 minus 92 squared by 92. And if you calculate the test statistic, we get 4.1374. This is my value. This is my calculated value of the test statistic. See in how many parts the sample has been divided into 4 parts. So my value of K is 4. So the degree of freedom will be 1 less than that, and that will be 3. Chi-square has its own statistical table. I have already shared the statistical table in the Google Classroom. You can find it from there. And there you find that corresponding to the degree of freedom 3 and level of significance alpha, which is 0.05, there is 5% level of significance, the tabulated value is 7.815. If I compare these two values, as per the rule given, the calculated value is much less than the tabulated value, and we cannot reject our null hypothesis, and we conclude that at 5% level of significance, the null hypothesis that the blood type distribution of people with stomach cancer is the same as that of the general public. So this is the preliminary class, and I have discussed the preliminaries of the chi-square distribution. In my next class, we shall deal with the chi-square test statistic with some other problems and with some other types. I hope that you have understood this particular problem, but doing one problem will not be sufficient. So after the class ends, you would read this particular topics, read this particular note in its entirety, and try to identify the relevant portions written over here. We shall meet in the next class soon. Till then, bye.